Microphone test. All right, welcome back, everyone. Did it actually cancel you last time? Well, I don't know why, to be honest. I'm also thinking about just making you a moderator if you're interested. Then you will never get cancelled. All right. What do we want to do today? Probably So what we want to do today is work on the constraint solver and especially work on the basic element constraints. By the way, GitHub has dark mode now after like hundreds of years. All right, I will not give you the responsibility. For like 5 seconds. All right. Stop me from spamming. So you agree that you spammed. That's also a good lesson. All right. Then, so this is the constraint we want to implement, which basically like this part. So it should basically create a new variable for C indexed with this, and then you can do whatever you want with it. And there are several steps we can take. So one is implementing the UI for this, which will be like hopefully not too difficult, but I haven't done something like that before, but I saw an example somewhere else. And basically this one should be translated into a constraint automatically and the variable should be returned. And then it's just a simple constraint, right? And there are two more constraints. One where C is a list of variables, this one, and the other one just the same, but two-dimensional. And the two-dimensional thing is actually what I want to implement to solve last year's Kaggle challenge, or like see how far we can go with the constraint solver for that. But at the moment, it's probably way too slow, and it can't even solve it in a simple way, like because of this. So let me also. Okay, that's not linked. Wait, this one is implemented. We implemented that last time. So because there was an issue about it. By the way, so I want to post to the Slack if anyone wants to join. So there I mentioned this one. Elements constraints. So this is like the best syntax we want. And this is something in between. So currently I only knew how to implement this in constraints. But the other one probably isn't too hard as well. Well, actually, I'm just thinking the element constraint is always with this equal to, it seems like. But in my example, it was with small or equal to. Maybe we make that simple. But I also found something else. Which is from minicp.org. There we have. It actually starts with the 2D version, I think. Oh, this is so white. Wait. To check what this is. Is this the hard one? I think it's too white for me. Sorry. Oh, element 1D. Okay, yeah. So we want to have element 1D. Don't look at this white screen. Which is this. Okay. Okay, so we have so T is fixed, like my C, and we have this equal, so I will change the equal. Change this first, and maybe later I can do that. Just that we know what we want to achieve today. Okay, so we have this T given, we have T of Y given, Z is a variable. Although it can be a variable as well. So we have two variables and one constant. Okay. And we can filter. Okay, that makes sense. So we can filter the ones which aren't in Z. Oh yeah, I think my current, this one is currently stupid, right? What is it? Yeah. Okay, so we need another variable. Because this one can't be solved actually. Okay. That makes more sense. All right, so the filtering step sounds easy. So what is for each value in the sense? It's just the number of Okay, so that's the number of possibilities, and with the number of possibilities of dy, so in this case we have the 3. So this is basically just this one, right? I'm a little bit confused, to be honest. So we basically count how often that is possible for each z, and if one of them is 0, we can filter it. And I think this one probably means if 3 is not possible, then can we filter something? So 3 is not possible, so we can filter this, this. Well, they are actually different. So here we are filtering of dy, and here we are filtering of the. Okay, yeah. But that doesn't. So when the 3 is not possible, then we just check and we remove them. 5 is. Maybe I have to check this one again. So for I and dy, we choose this. Zero. Or for each value. So in these ends. So for 4. So we are computing this one, ti, I and dy. Is these. So we only have 1, 2, 3, 4, and 5. And T1 is, I think we are counting like 0 based, right? So T1 is 4. This looks so easy that when you read it, it's a little bit difficult. Ti equals to z. What is this step, by the way? Isn't that the... It's probably the... because the z doesn't make any sense. Okay, so at least not for me. So we are value 1. Oh no, value 4. Sorry. So we have y equals to 1. So 1, 4 is a possibility, right? That's why we have this. But what is happening in this part? Oh, there we probably removed the 1 from dy. I think that's all there is. And stable marriage. Okay, all right. So we have the 2 filtering rules. Now we have to check how we implement the constraints, basically. So what, like, this is the pruning step, and for the still feasible step, which is much easier, solved should be also easy, and stuff like that. Okay. All right. Let me. Oh, and also. So how is it done here with the element constraints? So here it's elements, so y equals array. Okay, let's do the same thing. Okay, so 1D constant. And then we want to have y equals to array of x. And that's basically is y. Is that syntax reasonable? I don't know, but okay. We don't need that too. And I think I will call it element 1D constant, just to be sure. Okay. Do I have constraint solver open? Yes. Master. Let's close some stuff. Feature elements. All right. And yeah, if you have any questions, please ask in the chat. So yeah, let's do the basic steps. We need to define the constraints. Oh, let's start with the basic model first. We copy this. using jump constraints. I think, wait, I don't know. Sometimes there are problems with const when using revise. So, all right. Now we have function solve elements constraints. Whatever. We have our basic problem. Optimize is it? Yeah. And we have number of solutions is jump solution. Why is there no? I forgot how it's counted. Result count or stuff like that. Result. Oh, it's this. Actually, nope. Let's do it this way. Number of solutions. Solution. ID x. All right. And we want to have val idx in CS elements 1d const. I know it's a terrible name. See. Do we? Yeah. Yeah, I think it makes sense to have this because then dispatch is easier. So when we call this, it should tell us that it can be found. Okay, it's pre-compiling stuff first. Well, it makes sense. Yeah. Maybe it's okay if I don't save stuff. So all different sets. So first of all, we need to create the sets. In this case, we will have, it's more similar to the table constraint actually. So I just call it an array, maybe. Vector of int should always be vector of int, and we have elements 1d const inner, const. Yeah. Normally I have sets as well. Okay. Anyway, elements 1D const. So what this basically, I need. Anyway, so I define it twice because internally I need this dimension, but I don't want that the user has to specify the dimension. So I use this this function basically sets the dimension for the inner constraints. And internally, so inner basically means internally. I don't know, inner is not the best name, but I'm bad at naming, so you get used to it. Let's call that e.array, and let's call that e for element instead of all difference, and e.array. So directly let this solve. I hope I didn't do anything wrong with the struct, because that's the one that's hard to change when using revise. But I used revise. That's why it's recompiling now. All right, so we have our error element 1D const. Why? Oh, damn! I of course missed this. To change everything. This is so bad. Okay. Next up is to define the constraints in this. So first of all, we need to put this here. We need to define that we support the constraints element 1D const inner. So here we specify a vector of variables, which means like this is the vector of variables, and this is the constraints, which is element 1D const inner. Then the constraint internals are always identical. We have to define this inner constructor. Elements and element 1D const inner. All right. So this is also all difference. Okay. That's just for printing how many constraints we have. So what is the current problem? I think that was like it's not the solver doesn't support this constraints, and now we said we support it. Oh, but I changed the struct again. Too bad. Too bad. Do I have to? Oh, I have to do one more struct. So let's do this here. Element 1D const. I think I want to call it everywhere. Element 1D const. Did I just copy it but didn't use it? And we have more structs. So all different constraints. So every constraint this is hard to read. I don't. Oh, I think I want to save one more thing in that. But yeah, basically this defines the constraints with all the constraint internals, which are the constraints ID, the function, the set. So set is vector of variables, function is element 1D constraint, whatever. The indices that are involved, which are 2 in our case, the possible values for the indices, which functions that constraint implements, whether it's already initialized, whether it's deactivated, and just for bounding stuff, it can also provide some bounds for optimization problems. But for now, let's do feasible. Okay. So what I want to do, I think, is I have this ZZAP, which is vector. How do I call this? Like number of possibilities for any good names or any good explanation. Number of possibility for setting. Hi Zof, how's it going? Number of possibilities for setting set in set equals to what do we call it there? T of y. I think that's what I need. Oh, perfect. Do you have? Is it? Oh no, I define it somewhere else. I saw that there was a new comment. Does that help? It was the last issue we had, I think. So now we have init constraints. Our init constraint struct is the first we have to implement. So this is element 1D const and element 1D. Perfect. That sounds good. So these are just, there are a number of functions which we want to implement. That's not what I wanted. This one we don't need actually, but this one is also something special, and we want to have that first. But we need prune constraints, so every constraint needs defined how it's going to prune stuff, which is quite long for that one. And we have a still feasible function, and constraint solved, and this constraint violated function. Those are the ones that need to be implemented, and some of them don't have to be implemented. Okay. So another error. Yeah, there's no prune functionality. That's perfect. Let's copy this over. And we have element one constraints and element d constant. And initialize by initializing sets up. Okay, so sets up is the first element. So z is basically constraints dot indices 1, and from the search space. So this one gives us the index, and this one gives us the variable. And then for val in CS values sets, no, I think we want to do this differently. So that's called, I think it's lower bounds. Basically, we only need to know how many there are. So num bounds is that upper bound minus that lower bound plus 1. And then we have constraints dot sets up is zeros integers num bounds. And return true. So return true basically means it's still feasible, and we should probably check that it's actually feasible. That's here. Okay, we are there. Perfect. Okay, maybe to do initial filtering. Okay. Next one is Prune Constraints. Basically, this someday I have to fix this log stuff, which I don't use anymore. Reduce the number of possibilities given the elements. Just the basic stuff. Okay, so now we have our two filtering steps. Let me show them again. So first of all, we check for every so we go over all the T's, and if it's not in Z's, then we remove it from the possibilities of Y. Yeah, so we basically I still have to. Think about that. Yeah, it's the same thing, right? So we check for every value in Z, how often it appears, and if it appears 0 times, we remove that value, which is what this does as well. Okay. Okay. So basically, for each value in the sets, value set, do set sub of B is the number of elements I in the Y, assume that equals array. Let's just use that formation. And then such that T of I is equal to Z, and filter that 0, remove from dz. Okay. And reasonable. So the question is, does it make sense to save all that stuff? Do we actually need the sets all the time? Can we do something clever with it by reusing stuff and not computing changes? I think we could probably do that once, and when there is a change, do we do that in some other constraints? Just check. Okay, let's do the easy version first. So for val in, so we have sets before. Y is the second index. Might even make sense to save them in this constraint, actually, because there are only two of them. We don't have to access them like this. But in CS values of sets, which is basically that part, and we have constraints. That's up. Constraints. That's up of shifted, val shifted is val minus sets dot lower bounds plus 1 equals so basically we have y value in CS values y, and I have to check how the possible count functions work. Okay. So basically we get the value y, then we have t is constraint dot array, set dot array, and then we have like this, t of y. Well, we should check some bound stuff, right? We should do that in the init constraint stuff. So this one equals well, hi, Harvard random user 1. Can't remember how random. I probably just called you random all the time. Yeah. Why do I save? Why do I save this in an array? Does that make any sense? Because currently I would do like if that is empty, then do set sorry, feasible, or like not, yeah. Um, and return true otherwise. Kind of like this. So how is it going? Random. Okay. So there was no error with that. Just need to still feasible. So this gets called to check whether it's still feasible if I before setting a variable fixed. Return whether the constraint can be still fulfilled when setting a variable. Yeah, it's like general stuff. So what do I have to do in that case? So basically there are only two options. Either we fix Z or we fix Y. And there's also the option that it gets called without that anything of that gets fixed for indicate and verified constraint, but that's out of scope for today. So what I basically wanted to do is have this index, variable index, like that variable index and y variable index. Okay. And this one is fine. Okay. So if variable index is z variable index, so basically if we fix so if we fix this, we basically have to check whether z Oh, here we can check that sub, right? Yeah. But isn't that always feasible then? Because otherwise we would have removed it. We have to think about that for a little bit longer. But what we can definitely do is if basically we go over the values of y, so CS values y, and we have y val t y val equals to value. Well, value is the one we want to set. Else if true, otherwise that is actually the y index. So this means we fix. So this is just return z's, or like has z's the value of t value. That makes sense. Print solutions defines. Oh yeah, I want to print solutions always. Okay, so 1-1 is an option which is correct. Okay, all solutions. All solutions. All solutions. Okay, 1, 2, 3, 3 and 4 and 7. 4 and 7. Yeah. 4 is the index and 7 is. That works. Fascinating. Okay. Let's do some more interesting stuff. I don't know. Or like, okay, let's do this. We should get basically 7 solutions. Yeah. And this one will probably fail, right? Okay. So in the inner and the init, we should do initial filtering, which basically means, unlike the most initial one, such that this one doesn't fail, is that the index that we have is smaller is in the bounds. So what we can do is remove below. Oh. I'm just thinking that what happens with when you have different possible indices for that array. But I have a vector, right? I don't define abstract vector, so that I don't have to think about that. But okay. Because I think there has to be a way to get the indices, right? Somehow. But anyway, so remove below 1 of y. Still have this, and we have this. Return false, and above or length of set array. Assume indexing. Remove values of y which are out of bounds. Remove below. And I think I need to do this. Why? Okay, still 7 solutions. Looks great. Let's do a little bit harder test. Objective, and we want to maximize. What do we want to maximize? We want to maximize the value. It should still give us, and the other one is actually, and the best bound we can have is 12, and then it slows. Well, yeah, I don't know. It kind of makes sense because we want to have all solutions. But okay. Okay. So now okay, so we're the only ones who define. So can I use this? So basically I can move stuff, right? Yeah, okay. So I think I want to do this here. Initial filtering. And in this case, I actually want to just check the things we have changed for that. So what happens if we set the Zs? So if we change something of the Zs, then we have to double check all of them, right? No, then we only have to check that one. Yeah. What happens if we set the Y? Then we have to double check. We have to update all of them. Okay. Well, I think we do this. Anyway, where is this not highlighted? um, where do we do this? Constraints. Maybe for the table constraint. Table constraints. Something else. Changes. Oh, there we. Somewhere else. Why do I never use that there? All right. So the idea is that we set those once and then we update them based on what we have what was set. And what was set is saved in these changes, and we just need to have the first pointer we want to check in the changes. Oh, if you're still in the chat, Zob, thanks for the updates on the Jupyter integration. Just got an email. Well, the email is a little bit older, but not too much. All right, let's get it rolling. Why are you texting me that I am welcome? What did you do, El? But thank you. Okay, so okay, I think I want to change the structs a little bit. You can write tests and stuff like that. But yeah, I don't know whether I should commit this already to have like a basic working version. And then should check is solved and is violated as well. Yeah, I think I will do this first. Is everyone still happy in the chat? Or is it too boring what I'm doing? I'm quite happy with let's finally get working on this constraint, to be honest. I mean, the variable where t is variable, that one is the most interesting one. But we are getting there. Slowly but surely, we are getting there. So what I want to do is I want to test the constraints. So this is element 1d const.jl. And element 1d const. First, very basic implementation. 1d const. Perfect. And now this one can basically copy that. Oh, almond cream. Good. What a terrible name. Test it. Simple. So let's put this to 12 and put this to minus 12 to 12. Let's not maximize, but get all solutions. So this one should be 7, because all of them can be reached. Or maybe I want to can't be reached. And what's the best way to do this? Bounce, bounce. Possible results is tuple, and test status should be optimal. Okay, now push possible is index val and val, and now test. So index is 1, in possible. Then we have 2, 2, 3, 3, 4, 7, 5, 9. Yeah, I could do this programmatically because I have the T, but that's okay. All right. Let's do C. Pre-compiling. Oh, it's good to have a little bit of time to relax and think about the next steps. So yeah, I want to do the pruning and the still feasible stuff. Probably just the pruning faster by calculating it's only depending on what was changed. And yeah, put that into the struct. So I want to have the variables in the struct y and z. And I want to have like a pointer for the changes. Oh, I have to careful that I reset it. Right. Okay, I think let's write this down. Element on the constraints. So then we have z is a variable, y is a variable, and y. I don't know why I always start with that. Y index. Well, they started with it, so I do too. Changes pointer, and we have an arrow. It's perfect. And y changes pointer. All solutions not defined. Yes, I want to have all solutions. Let's save this. Okay, so the start pointer for checking like z dot changes. Still have an arrow. Okay. This is far shifted. What was this? I computed it, but I haven't used it. It's good that we have the test with the minus, because sometimes you just start with one and then you don't catch the errors. Wait. No, did I save times? Damn it. But okay. Didn't want to save that. Okay. So we have okay, I can probably just get away with this. And then in the init one, I want to have constraints.set dot y. Oh, because of that. Okay. Before we continue, let us run the tests. It's just super strange. I can show you this while we are waiting. Someone translated some of my blog posts into Julia, into some of my Julia blog posts into Russia. I really like this visualization. Looks quite funny. Yeah, so I didn't do this, but I wrote this blog post. It seems like I use different numbers for it, to be honest. Different colors. I have problems with English today. And some of it is so weird. Seems like some of it is not so strange. Is this actually? What did I actually program this? Oh, I actually did. Looks unfamiliar, but I like my colors more. Or maybe this is. No, I don't know what's going on there, to be honest. But yeah, it's quite fascinating, and a lot of people are reading this and clicking on my link, so they check out my blog, which is super nice. Like this one, I am grateful. Yeah. So he actually wrote me an email like a couple of weeks ago, I would say. This one looks like a Jarvis post, but actually this was before Jarvis. And I just used the Luxor stuff there. And this one looks like something I did in a Jarvis post, and I thought he might have mixed things up, but it's actually what I did. Anyway, just wanted to show that to you. And we passed the tests. That's awesome. We also did that already. Okay. Perfect. Okay, so what we want to do now is we want to speed things up by checking like which one was changed. Like we have change in Z, change in Y. And we also have now constraints, and constraints.y. Okay, So if Z is changed, that means and constraints.z. So basically for Z's pointer, or like change pointer in a length of z dot changes the backtrack index. So I think I should explain this. So basically changes save something like I removed value number 5 of Z's per each tree node we check in the constraint solver. And if we don't change anything, this is 0, or like this is an empty array. So we check whether we change something, and we can set this to this plus 1. So next time we call it, we don't check it again. Okay, then we have a change in Z's. So let's get rid of this. Which means if we have a change in Z, we want to, let me open this one again. If we have a change in that, then depending on what kind of change it is, like whether we fixed something. Okay, yeah, basically if we fix something, then it's easy because we only have to check that for that one, for a single value. When it's fixed, then it's simple, like it's the same speed as before. But if we remove one value, we only have to date. Oh wait. Wait a second. So basically, if we remove something from Z, which is like this case, then we remove values from Y, because that one will be kind of 0. I think we didn't even do that before, right? Did we? All right, see you. I'm a little bit confused again. So because this one gets not called for the remove value, but actually we want to remove this from. So if z, so yeah, again, if z is, if we remove z3, then we basically want to check in t which y we have to remove. That is this step. And this step is more for if we remove a y, then we remove values from z. Yeah. Okay. So actually, initial filtering for z. And the other one is basically we go over the values of yeah, so initial filtering for y. For value in y as values, if doesn't have like index. No, 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 no. Think and then quotes. So if z doesn't have the value, do I have t defined? Oh, I have here. T dot val or t val, then remove this from y. To why can I not jump? Sometimes I just don't get it. Okay, this copies it. That's what I wanted to know. Yeah, return false. Perfect. Okay, so again, change in z. If we remove Z. And then we have to go over all of them. If we fix that, it's simple. If we remove below or whatever, yeah, okay. Change is Z dot changes like current Z changes. Change pointer. So now, so this is this fix, remove, remove below, and remove above. So change type. I don't know, just call it change one. If change one equals to fix. So we fixed the Z variable. That means we have to go through all the T values, and if it's not like we have to go through all the Y, val, and CS values. Why? If T of Y value is not equal to upper lower bounds. Yeah. So change 2. And then we remove that again. Y. Oh, yeah. Return false. Okay. Else if change 1 is remove. I don't know, change type is easier to read. And change val, maybe. Change type. And change val. Okay, if we remove the value, and then we basically do the same thing, but if it's there, then we remove it. It's a little bit hard to read. We will refactor this later on. Remove above. So remove above, switch means if that's greater than, and we remove below. By the way, restart this one already to do some runs in between. Smaller. Okay. Let's run that. And I will be back in a second. I will get some more water. Enjoy the pause. All right, I'm back, and we have an error with some bounds checking. Oh, what is this? What? Why do I use plus? Oh, no. Today. I just put the links. Okay, we are still getting our 7 solutions, but we are probably doing some more nodes. No, actually not. We're doing loads less of them. Okay. Oh yeah, we will remove some stuff at the beginning. This. Okay, so we have the change in y, which means, let's have a look. Again, concentration is going down. We have the change in y. So for example, 2 is not possible anymore. Then we would do just have z sub of this value -1. And in the end, check whether it's 0, I guess. Directly check. Yeah, I don't know. No. So we probably have the same case. This copy pasting stuff is just not nice. Okay. You are there, and this current white changes. Why? Okay, so if it's a fix, and then we can immediately fix that. Fix car, and this again, if it's not feasible, then return false. Fix. Z to T of change. Okay, if we remove this, we can do that zap of T change val -1. Or maybe that's not. Like this should be also set lower bounds +1. Actually, I don't want to deal with that now, but it might be interesting in the future to just have like set the indexing of sets up differently with a custom array. Okay, so okay, remove above. What remove above means is that remove above. Oh no, but for val in change val +1 length of T. And val this one. And for in this case, we do 1 to change val -1 and white pointer, white changes. Okay, we actually want to remove stuff. So for I in 1 to length of that sub, if that sub, like if like counter maybe, if counter equals 0, then I like set val shifted. This means remove z val shifted plus z lower bound minus should be it, and return false. Remove z values where z is val, where z val, z zap val is equal to 0. Status infeasible. It's not great. Okay. Wait. So if that val shifted is 2 and the lower bound is 1, then lower bound is 1. Okay. If it's 2, yeah. Oh, we only want to remove this. Yeah. Okay. Wait. Actually, let's do this. Z val in CS values. So removing fails if the value doesn't exist. That's the problem in Z. And if Z zap of Z val minus Z lower bound plus 1 is 0, then remove Z val. This can be potentially. I think we still want to have 7 solutions, right? If I remember correctly. So 1, 2, 3, 5, 6, 7. Index maybe 8, but value. Okay. So something is going wrong, and like this one is very concerning. Oh, correct. Right, I know. Because we are increasing the. No, actually, I don't know. It should remove less. Things are getting a little bit more complicated with this version. So one thing we are missing is we have to reset this pointer when we are done with the step. That's one point. And another point is when we reverse prune, we have to reset that up. But I don't want to copy it, so I want to. So where do we do that? And I don't know whether this is actually the like this means that up of 1, 2, 3, 6, 7, 8, 9, 10, 11, 12. We have Z. So our value between 1 and 12. And we say that 12 can be like Y. Like the Y value 7. But why does this? Oh, okay, we can remove stuff. And if that's not possible. No, it's still happening. So it's from this. 2, 4, 6, 2, 4, 6, 1. Sorry, I'm talking German. 1, 2, 3, 4, 5, 6, 7. Why can we remove the 7 already if it's already removed? Remove from why? Oh, and we don't call that again. Okay, there are several things that I have to think about. One is, why is this weirdness happening? So why do I remove a value several times? And I have to reset the pointer, and I also have to reset zsub, recalculate zsub when we jump in the tree. Oh, that's the no. Oh, okay. I think if we do this, that might help. Oh, and why do we only have 6 solutions? Like, that's the other problem that we have. But maybe because of the zsub reset. Okay, so what we need to do, I think table constraint implements everything that's possible. Prune constraint, finish pruning constraints is what we need. So this gets called when we are done with the nodes. We're done with pruning. Element 1D constraints. And here we just have to set that constraint constraint set changes pointer to 1 and when changes pointer to 1. We only have one solution. Okay. That's okay. We're not done yet. Reverse pruning constraints. Does it get cold? So We call this reverse pruning. I always have O moments. It's just remembering. Sometimes it's remembering where I commented it. I have to think. It's not actually what I want. Actually want. So I want that when I check out the nodes, the very first time I want to reset something. But I only want to do it when I jump back, actually. But I don't. Oh, maybe it does. It does make sense. After backtrack. Yeah, okay. So then it should be okay. That was a helpful comment. So I have this with okay, and what I want to do here is recalculate, these up constraints, like constraints. That's all. This function, and I did this already. There. So we have Z, and do we have Y? Yeah. Constraint.Z and constraint.Y. Or reverse pruning. Does reverse pruning. We just want to calculate stuff. Okay. Oh, and we don't need that. Do this. This is where we got it from. We just have to be and now we can do that. T not defense. T is constraint. Damn it. Set dot array. And we are back to 7 solutions. Yes, that's good. That's very good. I don't know whether we changed some struct in between, but I don't think so. All right. And we have our error. Okay. Our test. So we remove 8 from y, which is this, and 15 is not even there. So, but we removed it in the first step, which makes sense. So we have to check this here. So if one smaller than length of t. Oh, okay. Let's do like another 30 minutes, and I will try to implement the nice version that you can write it in the nice form. Faster pruning. Okay, and I think did I change? Okay. No. Because 196. Then I can write down a list of what we have to do on the const. Forgot the closing words again. Solves, resolves, closes, fixes. Okay, closes. Closes 196. For test cases, in indicator in files. No. What else? Nice job. Syntax with what did I have? Z equals T file. Maybe some refactoring in general. Yeah, I don't know. Something like that. Okay. No. No. Oh, actually, back to this one. So actually, we don't need this. And then we want to have this here. Some supports for element constraints. 1D elements. I don't know. So we actually have int the owner model of I, yeah, X is the new variable. So we have oh, this one is actually different. Or is it? No, this time it's so we have X, we have our current variable, like X, current variable in CS elements const 1D 1D const. How did I 1D const probably, right? So and this is the vector. That's it. Yeah. This is what I want. Okay, now we have test cards. So now we have val equals to x index c. And I should probably do something because this creates a new variable which then is equal to that one. But okay. No. Okay. That is also true. Oh, it has to be bounded. Has to be bounded by the min and max. Is there some extrema? Did I do wrong? But okay. Yeah. So it has to be. Oh, it has to be this. So min val max val is extrema of a. Min val smaller equal to max val. Great. How do you like that? Why is this not changing anymore? But I mean, it's somewhat like this more, but it was different before. And why is this still yellow? But it works. That's so nice. That's so nice. Now I want to do something with a little bit more fun. How do we do this? Okay, so what can we do with this? Can we do sorting with this? So indices 1 to length of C and length of C. And value probably the same. But with like min of C, minimum of C, maximum of C. Okay, and now our constraints. Like basically for I in one length C, we have the constraint seconds. So basically we want to say please change to English keyword -1, and then we want to have val I is smaller or equal to val I plus 1. This is so weird. By the way, I don't like this yellow. I don't know what it does, but I don't like it. No. Oh no, this is not good use. But I hope my everything works fine. Okay, I think that's back. So this is such a weird way of sorting, if this works. And then we have constraints val of so actually this time we have to go for all of them. Value of so C of value of I, C of index of I has to be value of I. And I don't want to have all solutions. Get rid of that for a second. Includes. Let's do this. Element 1D constraints. Is this an efficient way of sorting? Probably not. But maybe it's a way. So bad. It's already sorted. So this is an M, and let's shuffle up. I don't know, 7, 2, 4, 6, 9, 10, 12. Why is there this one already sorted? So bad at generating unsorted lists. All right, let's do this. Oh, Why does it call? Oh, because it's a macro. Okay. Solve element constraints. All solutions to range. There should be only one solution because they're all distinct. Okay. Oh, wait. How do I do this? Oh, there's probably something like upper bounds, lower bounds. Okay, so this should be actually integer is true. Lower bound is min-val and upper bound is Maxwell. Maxwell, it's nice there. What did I just do wrong? Can I not do this? I'm confused. Oh, the objective function should be gone. Any problems? Are there any other problems? So, what is going on? Okay, now it started. Oh, yeah. No. Yeah, they should also be all different indices, constraints. Sometimes the solver outsmarts me. Index in CS diff sets. Okay, I think this should be mini, which is weird. That's right. Min. But why? Oh, that sets up. Why did it not do that there? So this is T. Why didn't it fail before? T val minus set lower bounds plus 1. Oh, and also, okay. Val wait, yeah, T val shifted. And then which means my first test case was not good. Nice! This is great. That's so nice. We have sorted an array. Okay. Oh, wait, how do I do this? Yeah. Okay. So rent 1 to 100. Like 1,000, and let's 50. Well, it takes 0.23 seconds to sort 50 elements, but it works. So I think that's quite fun. Test set sorting again. It's we should probably not do it this way. Is there a nice way of doing this? I could do rand 1 to 10,000 and then seed, right? Or random dot seed. Using random dot seed. Yeah. I think that should work. So seed is random.seed, no, rent 10,000 random.seed seeds print line seed for sorting test, and I should be able to reproduce this. And what else do we need? We want to have a test jump termination status is optimal, and test is sorted. Jump dot value. Actually, I don't have to do that. Val. Right. And test is also values and indexes values, and C indexes should be values. What happened there? But then I should do this. All right. And from test case. I have no idea what that meant. Oh, that worked. That worked out nicely. I just want to use a different setting, which is probably CS test optimizer. And here I want to have logging. But do I have something defined? No, actually. Let's. Oh. Oh, CS jump test optimizer. I actually thought for a split second, actually for a couple of seconds, that the constraint solver has an error. I can't believe how, I don't know. It's just this weird moment of realizing that you can do something as simple as sorting with this. It's kind of fascinating, and I don't know. It makes me happy. Um, Sorting, like MOI, nice syntax for elements constraints plus sorting test case. Oh, and some bug fixes, but that's all right. It's probably, I don't know, the best thing the solver can do, besides solving pseudocode. Is there something else we can program as that? Any ideas from the chat? Anyway, I just want to check, like, sorted things, I guess. There's simple constraints of value 1 is smaller or equal to 0. I don't know. And I want to solve actually solutions. So it's nothing to do with that, by the way. Oh, and the other one was just all the possibilities for val. Okay. So val 0. I don't know. Index is 1. Greater equal to 0. 3 possibilities, 2, 3. All right, we can do sorting. Yeah, and maybe I will get back with even better things to do. It's fascinating that what is this? Let me check. Number, like lines or codes. Calculator, Linux, I don't know. Oh, clock. Yeah. Do I not have clock? I don't know how to use it. No. I don't even have any. Where do I have CSS files? Oh, I should probably do this, but the others are test cases. But there's no CSS. It's coming from. But anyway, so I programmed a sorting algorithm in 7,000 lines of code, which is even very slow. But it can also do other stuff. So anyway, that makes me happy. And the last thing that I want to do is check this out. And to maybe also mention that here. All right. That's about it for this stream. Thanks everyone for watching. Special thanks to my Patreon subscribers. So if you enjoyed the stream, if you enjoy my blog, opensource.as, please consider subscribing. And you can see the Patrons here, the patrons here who spend more than $4 per month. So if you want to be awesome, you can see your name here if you spend that much per month. All right. See you everyone in the next stream. Maybe tomorrow, maybe not. I don't know. Doing maybe some refactoring in between. All right. Thanks.